So today we're going to be doing insert, delete, get random in O of 1. So the question is to implement a randomized set class, and this set class is going to just initialize a random set object. We have three operations that we can perform on it, which are insert, which inserts a val into this random set. We can remove a val from this random set, and we can get a random value from this random set. There are also some edge cases, so if the value already exists in the set, we simply return true, and otherwise we return false after inserting the value. And conversely, in remove, if the value is not present, we return false, but if it was present, we return true after removing the value. And this question is looking to be implemented once all three methods implemented at O of 1 time complexity. So that just means that we're going to have to do some overhead work in some space-heavy data structures, which allow insert, remove, and get random to be completed in O of 1 time. So let's think about this. Suppose we just have one simple data structure like a set or a list inside init. Then insert would obviously be, for a set, it would be O of 1 because we can easily check if a value doesn't exist in a set in O of 1 time, and if it doesn't exist, we can add it in O of 1 time. Remove is going to be kind of tricky because to remove something we have to look at all elements in a set or a list in order to know if we need to remove them. So that's a bit tricky. And then for get random, I think getting a random choice knowing a list or given a list is on average O of 1 time complexity. So that should be simple. So insert and get random are simple, but remove needs a bit more work. So suppose instead of a set we had a list, so we can just call the list self.vals, which is an empty list. Now in remove we need to know which index we need to remove or replace with another index to effectively remove that val. So to do that in O of 1 time, we would need another data structure, which would be a mapping between values and their indices. So we can have self.vals or val2 index, which is a dictionary because that's O of 1 lookup. So let's start implementing, and then we can come back to remove and see how we can leverage the dictionary to do O of 1 removal. So insert is pretty simple. We simply do if val in self.val2idx. If it's in the hash map, we simply return false, right? And we otherwise add it to self.vals.append val, and we need to set the index in the hash map, so self.val2idx. Let's put this up here. Well, this should be equal to the length of vals, so that would be the index. Okay, and then we can return true. So that's pretty simple. We simply add the value and then add a mapping to its index. Let's ignore this for now. For this we can just use the random library, and we can just return random.choice self.vals. This is just going to return a random choice from the list of values in O of 1 average time complexity. So finally we have to think about remove. We can start by just adding the return statements for the edge cases. So if val not in, if it's not in the hash map, we can return false, and then we need to do some calculation and then return true to remove it. So the question is, how can we remove the value from the list along with the hash map? So we know we're going to need to retrieve the index of where the value is located, so we can do index is equal to self.val to index of val, and we also know we're going to need to remove it at the very end from the hash map. So we can do delete self.val to idx of val. So the question is, how can we remove it from the list? So I think the approach here to do this in O of 1 time complexity would be to replace whatever index we need to remove with the last element, and just simply remove the last element, because with that implementation we would not need to adjust all the remaining values in the list, because we don't want a hole which would require all the later values inside the list to be shifted. So to avoid the shifting, we can get the last element. So last element is equal to self.vals of -1, and we can replace self.val to idx with the last element. And then we can remove the last element. So let's just double check if this is all that's needed. So we get the index for the value we need to remove. We get the last element, which we can replace at that index. We perform the replacement, and then we remove the last element in the list along with its index mapping. I think we also would need to update actually no, we don't need to update. So let's try this. I believe it should work. Get random. Okay, so we remove one, but one did not get removed. So I believe this looks right. Self.val is append the value and set the correct index. So the issue must be in here. We get the index that we need to remove. We get the last element. We store the last element at the index we need to remove. This looks the wrong way. Should be last element. It should be the index. And then we remove that last element from the list, effectively because we replaced it with the element that needed to be removed. We delete the reference to the index for that element that needs to be removed, and then we return true. So that should fix it. There's another issue somewhere in here. So get the index to be removed. get the last element, we set the last element's index. That makes sense. We remove the very last element and delete the reference. So what are we missing here? Yeah, we should not have 1 because we removed 1 already up here, so the only choice we have is 2. So when we're doing random to choice, we somehow have 1 left over. So if val is not in here, we cannot remove it. So we do this. Get the index. Index is being set. And the value is being set. We get the last element. We update the last element to have an index. And we also, I believe, need to store it. So I'm not storing it anywhere. So I think it should be self.vals of idx is equal to last element. So we store it. We store its mapping. We remove the last element. We delete the removals mapping, and then we return true. So that should fix it. Okay, submit. Cool. So we can analyze. We've already analyzed the time complexity. All insert, remove, and get random should be on average O of 1. The space complexity should be O of n, because where n is the number of inserts we could potentially do. So n is the number of inserts, and that's just because assuming we don't do any removals, we can have at most n items within the list and the hash map. So that should be it.